So we've seen electrolysis of molten ionic compounds. And when you do electrolysis of molten ionic compounds, it's pretty easy to figure out what the products are going to be because in the molten ionic compound, there's just one cation, one positive ion, and the cation will go towards the negative electrode, gain electrons, and get reduced into the metal element. And then there's one anion, so one negative ion, which will be attracted to the positive electrode. That's where it will lose electrons and get oxidized into the non-metal element. In the HL syllabus, you also have to look at the electrolysis of aqueous ionic compounds because really it's a lot easier to have a solution of an ionic compound dissolved in water than it is to have a melted ionic compound, which requires a very, very high temperature. The issue is in an aqueous solution, in addition to the ions, there are also lots of water molecules. And water molecules can also undergo oxidation and reduction. And so what that means is that if we're going to predict what's going to be made in the electrolysis of aqueous ionic compounds, then we have to use table 24 again and the standard electrode potentials. The key idea to remember is that the more positive an electrode potential is, the more spontaneous that process is. And on the flip side, the more negative an electrode potential is, then the less spontaneous that process is. It's related to the value of Gibbs free energy change, where negative Gibbs free energy changes are spontaneous and positive ones are not spontaneous. But since we are looking at electrolysis, which is a process where we force non-spontaneous reactions to take place, a lot of the electrode potential values that we're going to use here are actually, or that we're going to have to deal with, are actually negative values. And so we'll often be choosing between two negative values, and we'll be picking the one that is less negative, because by being less negative, that still makes it more spontaneous than something that has a more negative potential. So just to look at the table and point out the water half equations, which I don't think we've looked at yet. So the table always lists half equations as reductions. So it shows lithium ions gaining an electron and turning into lithium metal. So they're all written as reductions. The water reduction half equation, so when water ends up getting reduced, gaining electrons, the products are hydrogen gas as well as some hydroxide ions. And that has an electrode potential value of negative 0.83 volts. Further down the table, and a bit more confusing, as we'll see with the oxidations, because the table is written, everything is written as reduction half equations. In order to consider oxidation half equations, you have to look at these half equations flipped. So the oxidation half equation of water, the half equation that shows water being oxidized, is here's water on the right, and when we go to the left, we show the water giving away electrons, and that produces H plus ions and also oxygen gas. And the potential, because we flipped it, is no longer positive 1.23 as the table says, but it's negative 1.23 to go in that reverse direction. So the takeaways are that for water to be reduced or for water to be oxidized, both of those processes are not spontaneous processes. They both have negative potential values, negative 0.83 volts and negative 1.23 volts. But if you put in enough energy in the form of electricity, you can cause these different processes to happen. So if these are the half equations that are occurring, then you're going to see gases being produced at the different electrodes. And because it takes twice as many electrons to oxidize water, to make oxygen, as it does to make hydrogen, it only takes the one electron here. If you were doing an electrolysis where both of these processes were occurring at once, you would expect to make twice as much hydrogen gas as oxygen gas, because it only takes half as many electrons per hydrogen molecule. So you'd get twice the volume of hydrogen gas as you would of oxygen gas. So it's probably easiest to understand how to approach these when you're looking at an example. So if we were doing the electrolysis of aqueous sodium bromide, so sodium bromide NaBr, and both of those ions are just simple 1 plus and 1 minus, so Na and Br. So if this was a molten ionic compound, then we would consider that the cation would be sodium plus, And so in the electrolysis, we would say that sodium is going to gain an electron and it's going to turn into sodium metal. And that would be pretty easy to pick out as the reduction half equation. And then we would say, well, Br minus is the negative ion, and so the Br minus is going to give away electrons and turn into Br2, the element. And so that would be the oxidation half equation. The difference now is that in addition to those two half equations, we also need to consider the water half equations. So for the cathode where reduction takes place, which is also the negative electrode, we have to look for the reduction half equation of water. So here's the equation for sodium, and here is the equation for water. And what we need to consider is when we're looking at reductions, which is looking from left to right, so as they are written, which one of these is more spontaneous? And more spontaneous, again, is going to be less negative. So I think negative 0.83 volts is less negative than negative 2.71 volts. So the actual reaction, that the half equation that's going to take place for reduction, is the one that's less negative, and that's going to be this one. So in a solution where you have sodium ions, you won't actually make sodium metal in the solution as the product at the negative electrode. What you will make is hydrogen gas and also some hydroxide ions. Now that kind of makes sense if you think back to sodium and how reactive it is. And if you actually made sodium in an aqueous solution, the sodium would immediately react. Any sodium that was made would instantly react with the water to produce hydrogen gas and hydroxide ions anyways. So this reaction actually doesn't take place at all, and instead the hydrogen gas and the hydroxide ions are produced directly. So the observations at the negative electrode would be bubbling, and you could test the pH and you would see a high pH value, or an indicator would show a basic color near the negative electrode. So we aren't going to produce any sodium metal. We're actually going to produce hydrogen gas as the main product instead. So at the anode, it's the same exact idea. We have to consider the one we would have considered before for the anion, that was the bromide, but we also have to consider the water oxidation half equation. Now, the thing we have to do, though, is we have to flip these potentials, because these potentials, these positive ones, describe going left to right. They describe the reductions as they are written. But what we want to consider are the oxidations, the reverse reactions. So when I do that, I get negative 1.09 and I get negative 1.23. So of these two half equations, the more spontaneous half equation is actually the bromine one, because negative 109 is not as negative as negative 1.23. So I'm not going to do the water one in this case. I'm going to do this one. So the two half equations that are taking place in my aqueous electrolysis, water gaining electrons and turning into hydrogen gas and hydroxide ions. And at the positive electrode, we would have the bromide ions giving away electrons and making bromine. Now, if it's at room temp, then we would expect the bromine to just be liquid, because that's bromine's normal state when it's at room temperature. So it starts off aqueous and it ends up liquid. So the products, we would see some bromine, which is kind of this reddish brown liquid forming by the positive electrode. So it'd probably get kind of a cloudy brown color near that positive electrode. And you would see the bubbling around the negative electrode where the hydrogen gas is being formed. So those are the different observations that you would see. The ratio of electrons, it looks like it takes one electron to make half an H2, so it would take 2 electrons to make a full H2. And here it looks like 2 electrons would be needed to make a full Br2. So we would have a 1-to-1 ratio in the moles of our products being made. One final note, it didn't come up in this example, but it will come up in further examples. A lot of ionic compounds have sulfate as the anion, as the negative ion. But if you look in this table, there are no examples here where sulfate is getting oxidized. There is an example further up in the table, I believe, where sulfate is somewhat involved in a reduction, but sulfate can't really be oxidized because in sulfate, the oxidation state on the sulfur is already +6, which is really the highest oxidation state that sulfur can ever have. So sulfate won't undergo oxidation at an anode in the aqueous electrolysis. So if you are doing one of these examples, I know it's tricky out of context, but if you're doing one of these electrolysis examples where the salt has sulfate as the anion, then actually you don't have to look for two different oxidation half equations. You only have to look for water's oxidation half equation. So if it, instead of this being sodium bromide, it was sodium sulfate, then when you did the oxidation part down here, since there is no sulfate half equation, the only half equation to consider would be the one for water. And so the products would be oxygen gas and hydrogen ions. So it's just kind of a weird little note exception about sulfate. When sulfate is the negative ion, it does not ever undergo oxidation at the anode. And so instead, the one to consider is the one for water. So you'd be making oxygen and hydrogen ions.